The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone. Welcome to the fourth webinar in the latest Lab Automation University online series. Once again, I'm Kaylee Thomas, the Events Manager for Lab Manager Magazine, and I will be moderating today's webinar, which will focus on management's role in lab automation and technology management. During this webinar, we encourage you to send us your questions, and our speaker will address them during the question and answer session following the presentation. To ask a question, simply type your query into the question box on the right-hand side of your screen. At this point, I'd like to introduce our speaker, Jill Laskowski, who's currently the Executive Director of the Institute for Laboratory Automation, a nonprofit organization focused on the development of people and technologies to effectively design and implement laboratory automation and computing systems. Welcome once again, Joe.
Thank you. And the rest of you, welcome to the fourth webinar in this series. We're going to be looking, as Kaylee mentioned, on management's role in lab automation. Over the past several sessions, we've taken a look at what lab automation is, going right back down to definitions, and what technology management's about and why it's important. We also looked at how skills are changing because of the nature of laboratory work and the options for improving productivity. Now we're going to shift gears. We're going to look at management's role in dealing with laboratory automation. This actually is a fairly new role for management. In the past, laboratories and laboratory computing were divorced a bit from the rest of the corporation. But because of the nature of laboratory software, the growing importance of intellectual property management, lab management's got to get into the act and become part of the planning process. And depending upon the size of the company dealing with, that management may include more than just lab managers, but directors and corporate R&D. There are a number of reasons for it. Once upon a time, this was all that was concerned about with laboratory computing. But now that we have connections with other laboratories, links into process control and warehousing and shipping, and also the need for support from IT services, management's got to get involved to make sure that things are working smoothly. When we talk about management's role, we also have to talk about how laboratory automation planning gets done. And in our point of view, the first thing you have to do is develop a lab automation architecture. And that architecture has two components to it. One are policies and practices, the subject matter of basically of this webinar. The second are operational models, how laboratories are actually functioning, what the workflow was. And we covered some of that in the last session. The policies and practices provide a common basis of expectations for projects across an organization, basically making sure that all projects are being done according to the same set of rules and don't vary from one implementation to another. It provides a function similar to building codes in towns. In our town, if we want to go off and make some changes to the house, to a building, to anything that affects the infrastructure, it's got to be reviewed, licensed, and approved by the town. The point of that is fairly simple. If you're doing things that affect electrical service, water systems, or anything else, they want to make sure you do something that does not adversely affect their operation. We need to do the same sort of thing for laboratory projects, making sure they're done according to a common set of codes, a common set of rules, not only so that they don't violate anything that's going on in the organization, but also so that the project can be reused. If a project is being done in one laboratory and you want to reuse it in a second, you want to make sure you have everything in place so that you can transfer it and not have to reinvent the wheel. Management also has to be involved because those policies that are being developed have to be enforced and funded, and conflicts have to be resolved, particularly when you see differences in priorities between different laboratories and other organizations, such as IT services. Those policies and practices that we look at are listed on the right-hand side of the screen. We're not going to cover every one of them, but we'll cover most of them. And we'll begin by looking at asset management. Now, the asset management we're going to be talking about is not the stuff that accountants worry about where they put these little asset tags on equipment. But we're talking about the products of laboratory work, knowledge, information, and data. And one of the things management has to do is set goals to preserve the quality, integrity, and the value of those three elements. Quality and integrity, I think, are pretty well understood, but let's just go through it for a second. When we talk about quality, we mean that the products of laboratory work, knowledge, information, and data, are developed, collected, and managed according to clearly defined procedures that can successfully stand up to challenge. When we talk about integrity, we're talking about that those same elements are done according to validated processes, and that those processes can stand up to challenges. So between the two, we have proven procedures that have been shown to work and implemented in ways that work, people who are trained to do the work, and evidence that they actually do the work properly, and that the results can be trusted and used. Value is a different animal. We're talking about the products of laboratory work being maintained in ways that don't limit their use. Another way of saying it is intellectual property management, and worrying about, again, these three items. When we looked at this workflow model last week, we looked at these as being collections of data, documents, and so on. Now we're going to talk more about how they're actually being managed. And we'll do it via a simple example. When I was doing laboratory work, everything that we did was recorded in paper notebooks. And those paper notebooks had a table of contents, the work pages, and the signature block on the bottom that you signed when you finished the page or finished the work, and it was also witnessed and dated. Once that laboratory notebook was filled, we got to keep copies of the table of contents. The notebook itself went off to the library with a copy of the table of contents going to legal, and eventually it moved from the library into long-term storage. And for the organization I worked with, which was a plastics company, they went in boxes, paper boxes, and those boxes went into trailers. Places where the paper could be affected by weather, mice, mold, things that normally affect paper, which meant the life cycle of those paper documents was limited. If we look at it from the standpoint of cost and value, we can see a chart that looks like this. While the initial cost of the notebook is fairly low, just the price of the thing, the value continued to grow as we worked with it. As we added notations, experiment descriptions, experiment results, because of the value of that information, the value of the notebook itself increased. But at some point it became filled. So its value stopped growing, and we saw an incremental jump in the cost of in the cost of the notebook because of the cost of access. And when it sat in the library, no new information was being added to it, so its value was static. And then at some point, people decided it was in there long enough, and it was time to move it off to the trailers. And the cost again started ramping up because of storage costs. But the value started dropping. First, it dropped incrementally because of the cost of retrieval. If you wanted something out of that trailer, it wasn't easy to get. You had to know what you wanted. You had to know what box it's in. You couldn't really afford to go in there searching for it. And then someone had to go out to the trailer, get it, and bring it back. Over time, as people started forgetting the work that was done existed, the value dropped. If you have something of considerable value but nobody knows it's there, its functional value goes down to zero. And that's what happened. The same sort of thing happens when we deal with electronic media. There are some pieces of media on the screen that many of you may not have ever seen. There's some of it that we look at and said, yeah, I remember those things. I'm glad they're gone. And things such as the SideQuest disk on the lower left-hand corner may still be in use because they still have reasonable capacities. Another problem when we deal with the value of information is the ability to recover it. Most of us have heard stories about government organizations such as NASA or other archives where they have disk drives, mag tapes, paper information cards, and that sort of thing, but they can't get access to it because the readers that they need to work with no longer exist. It's also an issue about backup procedures. One thing that goes on is information gets backed up, usually through the IT organization. But one of the questions that's there is whether or not anybody ever tests the backup procedure to make sure it actually works. Local backup procedures are good for protecting against machine loss. Off-site backup procedures are good in case something may happen to the actual building. But unless those things are proven and tested to work, you have no idea if they're actually functional. The backup procedure may have been taken care of, but the ability to retrieve it, reuse it, and actually make useful work with that data may not have been tested. And until you do, you have no idea if it's ever going to work. Another issue that we need to deal with is the ability to work with the information. Make sure it maintains its value. Keeping the assets in a form that's easy to use and encourage reuse. Making sure that the cost of reusing those assets is low enough so that you actually do it. And also making sure that the chain of ownership is maintained in case there's a challenge. The movement to electronic media has a couple of purposes. One, you want to improve performance and the ability to work with it. And you also want to capitalize on the investment in research and test data. Information that's kept in paper notebooks, for example. People, as I mentioned earlier, often forget about it. You always hear stories about people who said, yeah, we remember somebody who did that kind of work a few years ago, but we don't know where it is. And often you find people going off and repeating the same set of experiments just to regenerate information that they had 10 or 15 years ago. One of the things we need to do is to challenge every step that's taken with the products that come out of laboratory work, with whether or not you're doing something that will adversely affect your ability to use it. The idea is to make sure we maximize the value and the ability to use the assets we have, while minimizing the cost by removing barriers to their use. What's management's role in all this? Well, part of it is a matter of setting expectations. Intellectual property management requires good rules for storage, archiving, backup and retrieval, and security. And they also have to make sure that people have the tools and the education to make it work. This is part of what management's role is in laboratory automation, to set the ground rules across the organization to make sure that these things actually function. Another area we'll look at very briefly is process management. We covered this in session 2, in talking about what lab automation was all about and the fact that it's built around processes, and statements that come out of things such as ISO 17025 that say that understanding the process in your lab is fundamental to automation and successful lab management. And on the quote on the bottom is from Frank Zini of Zymark, talking about you don't automate a thing, you can only automate a process. So as we mentioned, understanding what processes are, making sure they're well documented, they're well understood, is key to being able to deal with automation. Without that being done, you're out of luck. The issue of integration we'll be covering in the next section on November 27th. So now we'll move to a fairly important issue, and that's the issue of validation. There are two approaches to validation. One is retrospective and the other is prospective. Let's pick a point today and say that anything that hasn't been validated as of today, any procedures, any processes that go on, have to be validated, and those will be done retrospectively. It's not the best way of doing it, but if the work hasn't been done to date, that's the only thing you have left. Any new projects that start from today on would be done by prospective validation. That is, going through a formal validation process and making sure all the pieces are there to do the proper job of validation. But one of the questions that comes up is, what do you do when you're dealing with projects that are under development? How do you validate those? Well, the answer is fairly simple. You don't. What you're really talking about doing is prototyping a system. Systems under development, you have questions about how it's going to function, how it's going to work, what things are going to have happen. What you're really doing is building a prototype to test out those ideas and finding out exactly what's going to happen. You do the experimentation, you see what works, and then you turn around and use those results and everything you've learned from it, asking questions about, if we had to do this over again, how would we do it, what would we do differently? to make sure that you're building the best product possible and the best project possible. You go back and all that stuff becomes part of the user requirements. You have a prototype, you evaluate it, you learn from it, and then you restart the project. And that's when validation begins. When we talk about validation, we talk about a process that looks like this. This is from the Good Automated Manufacturing Practices. And if you want to learn more about it, there's a great deal to it. But you can look to the International Society of Pharmaceutical Engineers, ISPE.org, for more information about what they're doing. They have a number of training courses and a number of books on the subject that you can use. But we're just going to focus in on this one part, something called the GALP V. And the V comes from the shape of the diagram. The diagram itself is broken down into 3 sections. This is the section that talks about generating specifications. This is the section where the actual development and implementation gets done. And here we're going through and testing everything that's been done in terms of development against the specifications to make sure that things work. Basic idea is we generate user requirements, build the system, and then prove that it actually does the job it's supposed to, which is basically what validation is all about. The simplest sentence describing validation came out of the FDA when this whole program started, and that is having documented proof that something works as expected. The process begins by defining the user requirements and specifications. That's the customer's job. This is what we need. This is what has to be built. The customer and the supplier, which could be an internal group, are responsible for developing a functional specification. It's a response to the user requirements document and says, here's what we're going to do to actually make the system function. And it has to be agreed on by both parties. The users have to evaluate it to make sure that what's being proposed is actually going to meet their needs. The next 2 boxes, if I were to have to go off and look at them and design the GALP V, I'd switch them. Most automation projects involve software, and it's really software that drives the hardware requirements, unless you're dealing with things such as robotics, where you have to figure out what kind of robotics hardware you're going to deal with, as well as the control systems. But here again, you're using the functional specification to determine what hardware and what software are needed to meet the requirements of the job. Then we get back into the actual development of the system. If we're talking about software again, what the module specification is. Here's what each one's going to do. Here's how it's supposed to function. Here's how it's supposed to work. And from that, people go off and build testing programs. The modules are coded and developed, and then they're periodically reviewed and tested. And the entire system is put together and tested and evaluated. And at that point, the supplier's job, most of his work, is done, the development phase at least. Now we go through and we start going stepwise, going back up the other side of the V to make sure that all the stuff really works. Here we do software integration testing. Put it together, make sure it works, and test it against the specifications. Then we move into the hardware system, testing it, making sure everything there works, and testing that against the specifications. And again, if you're doing strictly a software program, you might want to reverse these, making sure the hardware works before you go off and test the software. Finally, all of the components are put together and tested against the functional specifications. At that point, the project is turned over to the customer, and the entire project is evaluated against the original user requirement specifications. And everybody hopes at this point that there aren't any surprises, because the customer and the supplier should be intimately involved in working together throughout this process. This is not an adversarial process. This is a cooperative process, people working together to meet a project. And at this point, you've got a completed project, and things are done. Now, anyone who is familiar with engineering will look at that and said, well, that's just normal project management. This is what an engineering project is supposed to be about. We've got the requirements, the functional specifications, design documents, and all of the components that go through, including acceptance, training, operational verification, which is this up here, and then putting the thing into use. Validation, properly done, is nothing more than a well-designed engineering project. And the success of that project will lead you to everything you need to work in a validated system. Management's role is to establish the project management policies that have to be followed to meet regulatory requirements. Basically, it's their job to go off and set the expectations of here's how we want things done. That serves two purposes. One, it makes sure that things are done according to preset criteria. Second, it helps anybody new to project management or dealing with projects in the laboratory to have a good idea of what it is they're expected to do. They're not sitting there with a blank piece of paper saying, okay, I've got this project, where do I start? They've got a set of criteria that are set up, and that can guide them through the process. Management is also responsible for instilling the idea that validation is not an end of project activity. It's not a case of where a project is done and now you go back and validate it. Validation starts as soon as you say, we need something done, and you start documenting what that is. It starts at the beginning of the project and is completed in parallel with the end of the project. Another issue we need to deal with is change management. Now, change management has two different faces to it. One of them is one you occur in project management, where change orders come down. Something has happened during the course of project development. Somebody realizes that something that was decided upon needs to be changed, and there's a formal process for submitting the change, having it reviewed, seeing what impact it has on the project, on costs, on schedules, and so on, and deciding whether or not that change is appropriate. But the change management we're concerned with here is different. We're concerned with the impact on people, making sure that the people in the laboratory are aware of what's being done, why it's being done, and how it's going to impact them. This is fairly critical. The people in the laboratory can either be part of the process, or they can look at it as something that's being done to them and dealt with it from an adversarial point of view. And I've dealt with both. I've dealt with cases where the people in the lab had no idea what was being done, and we didn't know that because we were contractors, and found out at the end of the project that they were resistant to signing off on it because they felt that their jobs were going to change or be adversely affected as soon as that project were put into place. I've also been involved with projects where we started the project off by sitting down with all the people in the laboratory and saying, here's what the project is about. Here's what we're going to do. Here's how it's going to affect you. Here's what we're going to do to minimize those effects, or how your jobs are going to change a little bit. And once they understood that, they became an active participant, and actually booster for getting the project done. They wanted to see it happen. So the key is, when you're dealing with changes in laboratory operations, you really have to work with the people that are there. You've got to listen to them, talk to them, make them part of the process, and learn from what they have to say. For example, one of the things we mentioned in one of the earlier sessions is that when you're dealing with processes, you should walk around and follow people who are carrying out the processes you're going to go off and automate. You'll learn from them. They may have some ideas about how things should be done better and improve your project, and find out while the requirements are being developed, instead of finding out at the end of the project. This next topic is important. We're not skipping over security because it's not important, only because we have a limited amount of time to deal with. Security is key, but we want to deal with some other things first. And the one we want to look at now is working with information technology groups. As fundamentally important as the science in your laboratory is, and everything that's going on in your laboratory is based on the science, in the short term, we're going to see more in the productivity gains as a result of doing work with information and automation technologies than we are with changing the science. It's this organization working with IT services and other groups where the real changes are going to be made. And we talked about that in the last session. We looked at options for improving productivity. But when you start dealing with IT services, it's easy for an adversarial relationship to start up. And that's something you want to avoid as much as possible, and it actually isn't that hard. For many departments, IT specialists are supporting the same kind of products and systems that they use themselves. There are things that they're intimately familiar with. They know how to use document processing. They know how to use spreadsheets, presentation software, and so on, database packages. So if an accounting department wants to work with something, the ideas behind what they're working with are fairly common and easily understood. The same with legal departments and word processing applications. The items on the right are from OpenOffice and provide pretty much the standard set of Office Suite software. The same things are available from other vendors. So these are things that IT people are familiar with. But labs are different. It's a different world, and it's a very much an unfamiliar world for them to work in. This is a photograph of the NMR facility at Princeton University. And if any of us were to walk in there and saw the equipment, we wouldn't be intimidated by it. We'd see the NMR, we'd see the tanks, we'd see the systems, and it's like, okay, this is the instrumentation we work with. But unless they're educated, an IT specialist will walk in and only see the computer systems and things associated with the computer systems. The rest of it is just background stuff, and they really won't pay attention to it. And yet, it's that background stuff that's important, and the whole reason why the computer systems are sitting there. The issues come down to some fairly simple things. In order to function, your laboratories are going to depend upon computer systems. The IT people supporting them may not understand how they're being used, what they're doing, anything about the applications. They walk in there, all they see is the computer, and they focus in on the things that they're familiar with, the operating systems, for example. It's also possible that the IT department has policies concerning those systems that will not work in a laboratory environment. We've mentioned it before, and I'll probably mention it again even today, that there are things such as upgrades, for example, to operating systems and applications that can cause, and database systems that can cause the actual running application, the thing you depend upon, to break. And we keep on hearing about this over and over again. IT policies and lab policies don't mesh. Those have to be worked out, and that's another reason why lab management has to work together with corporate management to make sure that those policies are set. Here's some things that you need to work with or you need to think about, and why working with IT is important to you. Because they have access to tools that you need. For example, do you have old, out-of-date systems sitting around that are there only because you need access to the data and data processing, but they're not actively in service collecting new data? They're just old systems. They have data on you need to work with, but you don't use them for anything else. When a new system is being installed, would you like to have a separate set of installations that are being used for training purposes? And this goes back a little bit to the change management issue. You want to allow people to sit down and work at a system, make all the mistakes they can and want to make as they're exploring the system without affecting the actual live system, so that you don't have to worry about audit trails. You don't have to worry about data being misentered. Let that happen on the training system and not on the live system. Would you like to have access to previous versions of a system while new versions are being installed or upgraded? Those are reasonable things to have happen in laboratories. Well, the IT people have systems available that can go off and do that. And one of them is called virtualization. This shows a diagram from VMware. There are other vendors that provide the same sort of software. The idea, and we'll go into it in more detail later on in this hour, is to remove everything from a physical computer system that's running on, say, on a desktop or a standalone version, and put it onto a server that can be accessed and supported separately, relieving the dependence on old hardware, so you don't have to worry about supporting an old 486 or what have you system sitting around, and that regardless of the operating system and the version of operating system can still be supported. Each one of these containers, and we'll talk more about those, actually is a separate computer, but it's all running on one system and on one server. All of the things that I just mentioned, the 3 points on the top of the screen, are things that can be satisfied and dealt with as a result of virtualization. In the last session, we talked about the use of multi-instrument, multi-user client-server systems for laboratory data. Client-server systems. Again, this is another reason why you need to have IT people involved, because they're going to be the ones who are installing and maintaining these systems. And you've got to work together to make sure that these things are done and done successfully. For example, one of the things you may want to have is remote access to a chromatographic data system. Do IT policies allow outside access to internal systems? You may have to modify those policies to make that happen. Basically, what we need to do is have a partnership between the lab staff and IT support in order to make things work. But there is one thing we need to be careful about, and that's that partnership doesn't go too far in one direction. There are people who simply say, our laboratory needs a particular type of software system, and then leaves it up to the IT group to go off and do the research, the evaluations, and make a proposal what kind of system should be used in the laboratory. That's a little bit too far in one direction. By a partnership, the tools that you're looking to buy are things that the lab is going to be dependent upon. The lab people need to be as involved with the selection of the process and selection of the tools and the products they're going to work with as the IT people will. Both of them have input into it. The lab people will be concerned with functionality. Does it work the way we want to? Does it integrate with the other systems that we need to deal with? The IT people are going to be concerned about support, evaluating the vendor and the vendor's relationship and ability to go off and provide support. What kind of tools do they provide? Are they working with current versions of operating systems and current versions of databases? So both groups have something to contribute to the problem. It shouldn't be just something of saying we need a product and have somebody else do the selection for you. It's like buying a car. You don't decide you need a car and hire somebody to decide what it is you're going to buy. It's cooperative effort. Making that partnership work means filling a gap between people who have very strong laboratory skills and people who have very strong IT skills, and making that come together. There are a couple ways of dealing with that, and we're going to talk briefly about two ways of going about it. In a small organization, a small laboratory, where either there is no formal IT group or the IT group does not actively get involved with supporting the laboratory, it might be worthwhile going off and taking someone who has, in the lab, who has a bent towards working with computer systems and elevating their position, training them to provide some level of IT support. There are problems with it, but it can be useful. One of the things you have to do to avoid the problems is not to simply add an IT support role onto the existing laboratory worker's workload, but to change the position. Recognize it as a formal consulting liaison position so that they're not treated as someone whose primary job is lab work and doing the support is secondary work, and if lab's goals are not being met, that somehow that they're seen as being lacking in supporting it. It needs to be understood as being a separate position. There is a problem though, and one is career path. Once a person steps into that kind of role, it's difficult to step back out of it. So they may find out that they're in an area where they're doing something that's interesting, but within their organization, there's nowhere for them to go. As the organization grows, that position may grow and become more interesting and more satisfying, but at some point, if they get frustrated enough, they'll leave. That person needs to have, in addition to the technical requirements for the job, needs to make sure they have good interpersonal skills. Most of the problems they're going to be dealing with are not technical problems, but people issues. And they need to be able how to understand that and deal with it. They also need to be adept at office politics. It always comes up as part of the job, and they may as well understand how to deal with it and put their egos aside and be able to work with it. Finally, they need access to outside support if they're going to do the job properly. You can't expect this person to understand everything there is about all the systems and the operating systems and software they're dealing with. They need to have access to resources to go off and support them. Some of them may be internal IT sources. Others of them may be the vendor sources. You have to make sure the support contracts are there to help them do their jobs. Another approach to dealing with the project, that issue, the filling that gap, particularly if you have a large enough IT group, is to find an IT specialist who is interested in laboratory work or at least curious about it, and train them to understand how laboratories operate, what the work is, how the work gets done, what the components are. The idea isn't to turn them into a scientist or turn them into a lab technician, but to allow them to understand what it is you're talking about, so that when conversations are held, the lab people can talk the way they're used to talking without having to try to convert everything over to computerese, and that the specialist can sit down and have an intelligent conversation understanding what's really being done, and that person has the authority to go off and balance lab and IT priorities. And that can be a very useful situation. You have to deal with the growth path, but if the organization is going to grow, that growth path will be more natural than it will be in the previous case. The benefits are these. They understand the IT technology, so the real job of support isn't a problem. And once they're trained, they'll be comfortable working in that environment. When they walk into the laboratory, like that NMR facility, they'll see everything there and not be intimidated by it or not ignore it. They'll understand what's going on and be willing to talk to people about it and work with it. Again, the requirements are very much the same. Good interpersonal skills. Most of the problems are people problems. And also working in office politics, trying to balance priorities and requirements. The only fear you have to have is for something like this is that the IT people may see them as being a lab person. The lab people will see them as being an IT person, and they'll feel a little bit uneasy as to exactly where they fit. Part of that can be dealt with by properly elevating the level the person is working with and making sure that they have the job recognition to take care of the things that they need. Management's role in this is setting the ground rules so that partnership between the lab and the IT people can succeed. They need to make sure that conflicts and conflicting priorities are resolved ahead of time, that everybody understands what the ground rules are, and that the goal is making sure that the lab has the tools they need to get the job done. The goal is not to provide IT people with an easy support path. The lab has to meet its goals and meet its requirements with the tools it has. The IT's job is to make sure that they all work. You also need to ensure that the people filling that gap have the recognition and authority to meet their responsibilities. And the authority piece is important. You can't simply dump the responsibility on them and say, but you have to negotiate your way through things. If something has to get changed, they have to have the ability to go off and make sure those changes are done. The next thing we want to take a look at is data lifecycle management. How long is the data that you have in your laboratory, how long does it have to be there? Is it years, decades? We gave a course that covered this topic a few years ago, and one of the attendees was from the military. They needed to have access to the data for 75 years. Basically, they need to have access to it as long as anybody who might be affected by it died. So how many product generations is that going to cover? Is there going to be a drift in the results? We're going to be looking at the layers of software that are involved. And as software, new generations of software come in, the software may change. Underlying algorithms may change. For example, if it's a spectroscopy software, chromatography software, p-picking algorithms may change. And that may affect results if it's applied to old data. If you have a sample that you know is rock solid, that's not going to change over time, and you analyze it repeatedly as through successive generations of software, will you get the same results? Or if the results drift, will you be able to account for that drift? If you have data files and lose access to the processing routines that created them, can it stand up to a challenge? Will you have data files that are really usable? Or will they simply be files of bits and bytes that have no value because the underlying software is gone? This goes back to the asset management idea, making sure you have all the resources there to support and make sure and take advantage of the data that you have. To many people, data lifecycle management is a storage management problem. It's an IT issue because that's where most of the discussions take place. It's issues such as changes in hardware, changes in systems, and backup procedures. But laboratories are a lot different than most typical business information places. Lab data is the end result of a process. The meaning of that data is dependent upon an understanding of the process used to develop it. The data that you have in your laboratories is a result of a process, and that's important. That process looks like this. Samples are prepared, processed, and then the computer systems get involved with data acquisition, doing the analysis, and doing the reporting. This is a fairly significant change from what we used to have going on. When you looked at a chart, when a human being looked at a chart and drew baselines and did peak measurements, we understood how the analysis was being done because the person was doing it. We understood how they were trained and what they knew. When you're dealing with software, the details of the algorithms that are used for doing the processing may not be available to you. Some vendors deal with it very well, others don't. Waters, for example, if you dig deep enough in their website, you'll find documentation on how their peak processing algorithms work. Other vendors don't provide that information. But you have to realize that what you're dealing with is software that's layered on top of an operating system and laying on top of hardware, and all those contribute to the execution of that process. As those systems change, you see a pattern like this. You see generations of computers and operating systems going on, generations of application software laid on top of those that may not be in sync with the changes in the operating system, and the data that's collected by them moving from short to medium to long-term archiving and storage. The problem that comes in is what happens if you're operating here today, but you need access back to this data back here and the way it was processed. Can you do that? Well, as I mentioned a few years ago, we wouldn't be able to deal with that very well, but today we can. You need to be able to keep and work with the information. Your need to work with the information is going to extend well beyond the likely life cycle of any product. You need to save as much data as possible and make sure that you're not limited by a vendor's restrictions on data access. One way to deal with that is the solution we mentioned earlier, and that's virtualization. Copies of systems running on servers. Comes back to this diagram that I showed you a few slides ago. A computer system consists of the application software running on top of an operating system running on top of hardware. Now, some of us will look at this and said, well, this is all just programs and data. But in fact, it's all just data. In a virtualized system, you can capture all of the data, and that's everything in this box, as a large file and store it on a virtual server, and then get access to it as though it were a physical piece of computer systems. You can log into it, you can run it, you can have access to it, even though it's simply a data file. And in fact, multiple people can have access to the same container running it independently. With virtualized systems, you have one hardware server or server system running multiple copies of applications and operating systems. And these operating systems don't have to be the same. If this server, for example, is running a Windows operating system, you can still support various versions of the Windows operating system going back to Windows 95 if you have to, and also support Linux, Unix, and the Mac OS. All that is possible within a virtualized environment. Basically, what we're really dealing with is time sharing, where you have one server, but each user can get into that system, log into it, access what it needs to work with, execute those procedures as though working on a private standalone machine, and get all the work done they have to do. The only restrictions are that you can't do any live data acquisition unless the virtualized system is set up for it, and that's up to the application's vendor. Most of them won't allow you to do that. This has a great deal of cost benefits because you can reduce the cost of cabling, hardware, support, and infrastructure. It simply makes things a lot easier. It makes the IT people a lot happier when they're dealing with that kind of environment. But also has a great deal of benefit for you. For example, let's go back to this example that we talked about earlier. You're here today, and you want to look at this data. Well, if this were virtualized, you can pull up all of the data, the application software, and the operating system for that particular generation and work with it today as the same way you would have 5 years ago. That allows you to take a look at any of the data and use it within the context it was generated in. And that's important because the algorithm that was used down here for doing some analysis may not be the same as the algorithm that's used here. It may have been improved or changed. And you really want to evaluate the data with the same set of software it was collected with, not against a new set of algorithms, because that may create a change in the data that you have to account for. The way you deal with this system and implement it is to go off and take a look at the system and say, all right, we're going to retire that system today. Send the virtualized system, tell it to go off and make a copy of it, pull it back on the server, evaluate the copy, and when it's done, this hardware can go away. You can still get access to everything you need here. But in order to do this, you need to be able to work with the IT people. All the virtualization stuff is going to be supported by them. So you need to work in cooperation with them to make sure that that stuff gets done properly, that you have access to the type of systems you need access to, and that you have their cooperation in working with it and setting it up. Management's role here is to set expectations for how things are being done, to making sure that the labs have access to the tools they need to go off and implement these kinds of systems, with IT supporting them and understanding what's going on, providing the resources, and also making sure that the policies are set up in place and the support is set in place to make that work. The last thing we're going to look at today is the issue of technology management. This is a typical product lifecycle diagram. Products are developed, upgraded as required, being put in the customer's hands, and then based on customer use, new product requirements are done, development is done, and you have a continuous cycle. This is a diagram you'll find in many books talking about product life cycles. It's also completely useless, particularly in terms of laboratories applications. This is a diagram that we've developed to go off and look at product life cycles, and it's important because it goes off and lets you helps you evaluate what happens to changes. For example, that previous diagram looks a little bit like this one. You have the initial concept, the product goes into development, it's released, goes into the customer's hands, the customer looks at it and evaluates it, determines whether or not changes need to be made. If so, yes, you get the requirements and do this. So that's fairly simple. But what happens down here if those changes are not feasible with the existing product? Then you have to evaluate whether or not the vendor has to evaluate whether or not a new product generation is justified. If it is, then that generation goes on and we go through this part of the loop. If it's not, then the product's retired. Or if the product is released and it fails in the marketplace, it's retired. These have different impacts on the way your laboratories work. If the product is a normal upgrade, it's a fairly low impact. If a new product generation is being developed, you may have problems with command sets being different, which means a lot of the software that you've developed to work with that system isn't going to work anymore. If a product's retired, then you've got to worry about replacing that product. If it's hardware, where are you going to get support for it? How are you going to get parts if something goes bad? If it's software, then you've got to worry about long-term support because at some point the vendor's going to stop supporting it. And unless you upgrade, you're not going to have a functional system anymore. The key is coming back to these workflow diagrams, generating them and using them as the basis for going back and looking at hardware implementations. But when we do that, we have to take into account the fact that every one of the products that we're looking at has its own life cycle, and that these life cycles are done asynchronously. They're not done in cooperation with each other because they probably come from different vendors, and even within the same vendor, they're going to have different life cycles. So there's a lot of work that has to go on when we start looking at planning for systems. The planning is not just within the standpoint of a particular product, but we have to look at the impact of life cycles on multiple products. Management's role in all this is making sure that the planning is done properly, that the coordination is done with other groups, that IT groups are involved and provide the support that you need to get the work done, that cooperation is done with other laboratories so they understand what's going on in your laboratory and any linkages between the software you have running and the software they have running is working together. Where it's appropriate, standardize on products. If you're working on limb systems in multiple laboratories, if you can, and if the requirements match, try and standardize on those limb systems. It'll make the support problem a lot easier and probably reduce the overall cost of purchase. And again, data formats. Try and standardize those wherever possible to make the support better. Another area where all this becomes important is outsourcing laboratory functions. This has become a fairly common thing in many laboratories where work is outsourced. One of the things we have to do is to make sure that the outsourced laboratory is managed within your facility according to the same policies and practices that were set up for internal operations. So management's role in lab automation planning, and we've gone through this stuff a little bit quickly. If you have any questions or want to contact me later on, just send me an email and we can talk about it. But management's role is to set goals, define policies and practices, make sure that we have models of how the labs are operating so we can go off and determine what products are appropriate. Reviewing project plans against goals, making sure compliance requirements are met, that technology management and coordination is done, that people understand what's going on, what kind of changes are being made, and that they're part of the change and not something that's happening to them. Also resolving interdepartmental issues and providing an environment that enables people to be successful. The next section is going to build on what we've talked about today and look at areas such as integration and paperless systems. What's realistic, what isn't, what's feasible, and how to go about dealing with it. Any questions?
Thanks, Joe. Yep. Our first question is, you stressed both information and data. Is there a difference between the two?
Yes, there is, in laboratory applications. If you were to walk out on the street and talk to people, the words information and data would probably be used interchangeably with no distinction between them. But in laboratories, there is a difference. If you look at a chromatogram or a spectra, data that's taken as part of a series, each data element by itself has no meaning. The 40-second point in a chromatogram doesn't mean anything unless you look at it in relationship to all the rest of the data. Where a pH measurement, which is a piece of information, or the end result of a chromatographic analysis, the concentration of something, actually does have meaning. And these are not trivial distinctions because they do have an impact on how data is being stored. The instrument data is being stored either within the instrument computer system, or an external server. The information, which is the condensed version of all of that stuff, may be stored in an electronic laboratory or notebook system. But in order to back it up and support it, you need the linkages back into those other data systems. You also have to understand that those definitions that go, for example, what you define as being data and information in your laboratory may not work once you move outside the laboratory walls. Once, say, for example, you're doing some testing and you generate information as a result of that testing and send it off to a research lab, or if you're in a quality control environment, send it off to manufacturing, they may use it as simply a type of data. So that context is going to change, the definitions and how it's being used are going to change. But they need to still have the same traceback. Once they have a piece of data or information in their facility and there's a question about it, it needs to go back and be able to trace back to all the data and supporting information you have in yours. So yes, there are real differences, and they have an impact on how you store information, how you store these things, and how you access them and where these things are stored.
Okay, and then our final question, unless anyone has any more that they want to send in, why are you emphasizing planning with digital systems?
All right, when we, give me a second here. When we started talking about laboratories maybe 15 years ago, we used instrumentation, some of them that had processes in them, but the results were usually recorded on paper. If we ran a spectra, the results of the spectra were recorded on paper. Chromatograms were recorded on strip charts. Everything wound up on paper. So basically, the thing you had to manage was how you're going to keep track of the paper, how it was going to be indexed. You could change the instrumentation, but the end result was still paper. So everything was in a fairly common format, a format that was easy to understand and work with. When we start talking about digital systems, you start having information being stored in multiple places and not in ways that's compatible. If you're going to change a system, you need to be able to understand what's going to happen with the data that's in the old system, how it gets transferred, if it can be transferred to the new system, what formats it's in. And now all of a sudden, instead of having everything in one format that a human being can understand and work with and check on, you have things stored in multiple formats, different systems, and you've got to start worrying about how these things are going to be archived, indexed, accessed, and managed. As a result, we've got to spend a lot more time thinking about how we deal with systems, what kind of vendors we work with, what's their history, how long are they going to be able to stand behind a product, what happens if product changes. It's because the data is part of a number of different systems, and you can't separate the data from the software because you need the software to look at them, that you've got to do a lot more work on planning. You've also got to do a lot more work on thinking about how you use the systems. When we work with chromatographic information on paper, you looked at every chromatogram. If there was a stray peak, you saw it. If a peak didn't look right because it was a shoulder, you saw it because you were drawing the baselines. Now we're used to seeing printouts that give peak information, peak areas, peak retention times, and the results come out of the computer and you believe them. But one of the things you've got to worry about when you're using these systems is, do you have alarms, for example, that will say you're expecting 7 peaks and you got 5, or you got 8, that something was missing or something showed up that may be a contaminant. Or, for example, you're expecting a separation to be a baseline separation, and it turned out to be a valley separation. That either means that something was wrong with the chromatographic processing, or that there was contamination there. So since we're now shifting a lot of the burden of the processing to a machine instead of a person who's making judgments, we've got to be a lot more careful about how things are done, spend a lot more time planning things to make sure that we're still getting good, valid results.
Okay, thanks, Joe. This brings us to the end of today's webinar. Please consider reaching out to Joe directly, as he is the true expert in this field. His contact information, as you probably have received, can be found in the emails that he has sent to you with the password and login information for today's webinar. Once again, I would like to thank you all for taking the time out of your busy schedules to join us today, and we look forward to seeing you back here again. Goodbye.